Good day all, and thank you for joining our webinar. My name is Marit and I will guide you through the workflow of climatic loads, more specifically the 3D wind generator. Today we will use three examples to discuss the different settings and the generation of the wind loads itself. In the topics for today, we will first discuss some general settings of the 3D wind generator, as well as take a further look into the wind data and how openings can be taken into account. Next up, we will take a look into the generated wind zones and how you can manually edit them when necessary. These settings will be checked for a rectangular building. Our last model will discuss a canopy structure. At the end, I will briefly discuss the interesting information you can add in the engineering report. In this example opened in SCIA Engineer version 25, we will discuss a steel hull building. It consists of 1D members, columns and beams, and the building is closed off with load panels to which we will generate the 3D wind load. On the long end of the building, you will also find two large openings with an awning on top created with 2D members. The wind only needs to be generated on the outer panels. So to make our webinar a bit more easier to follow, I will hide everything I do not need based on the layers. In this model, only the outer panels and the two plate members are added to this panel layer. Now, when you want to use the 3D wind generator, you need to activate a functionality in the project settings called climatic loads. Without activating it, you will not find the wind properties at all in your project. Now that this is activated, we tell SCIA exactly on which elements the wind needs to be generated. This will be all those load panels and 2D members which are visible on screen. To tell SCIA the wind needs to be generated on these panels, we activate 3D wind in the properties of the panel. This will add wind data to all of these members, which is indicated with the small arrow on the side. To make this a bit better visible, I will change the scale so that you see the created arrows. You can select the wind data by clicking on those arrows to check the different properties. One important property is the type that is selected, because that refers to the code and defines which zones need to be created on this element. You also find friction force, swap outer surface, and openings in these properties. Swap outer surface will be quite an important one. This is important to define the outer face of your elements. Right now, you will notice that all arrows visible on screen are following the positive direction of X or Y. Now, for two of those walls, that arrow is pointing inwards our building, and that arrow actually needs to point to the outer surface. To change this, you can use either the option Swap Outer Surface in the wind data as you see now, but if we select the load panel itself, you will also find that this option, Swap Orientation, is also present. Both options are similar, but the difference is that for swap orientation in the load panel properties, that the local coordinate system will be switched as well. To show this, we can activate our local accesses of the 2D members to visualize this. Now that this is visualized, you see the local coordinate system of each member, and the wind data and the local coordinate system have the same direction. It follows the positive z-axis of each member. If we now swap orientation with the panel properties, you will notice that the z-axis will point in the opposite direction, as well as the wind data. For a load panel, this does not make a difference. For a 2D member, it depends on how you would like to check the internal forces. If you do not want the local axis to be rotated, then I would suggest to use the wind data and activate swap outer surface, because now the local coordinate system is not rotated. Let's toggle off our local coordinate system since we would not need that anymore. Another property we need to discuss further is the type property. The type wall or roof will be assigned automatically based on the orientation of a member. So it will recognize the different types wall and roof, and for a roof it will even recognize that it is angled, and therefore instead of the type flat it will assign the type monopitch. In this case though, it is actually a dual pitched roof, so we will need to change that manually. Other types like a canopy or an awning will always need to be assigned manually. In the next properties, you can activate the roof overhangs and the friction falls. For this model, we will activate the friction falls. And you will notice now you can select the surface type. You can either choose smooth, rough, or very rough, and it will influence the friction coefficient. Let's use smooth with a coefficient of 0.01. For the awnings on the side, we can do exactly the same thing. We select our 2D members and we firstly activate the option 3D wind in the properties of those 2D members. This will activate the wind data so that we can take a look into the different types and eventually generate loads on them. In the wind data of these two members, you will find that the type roof is assigned automatically, but because this is an awning, we need to change this manually. Similar to what we find before, also friction falls or swap outer surface can be used for an awning. Now that we have set up all parameters for these load panels, we can take a look into our annex settings on the top right. With these settings, you can define some code parameters, and we will specifically take a look into the wind actions tab. We start with the 3D wind properties on the top, where you find that you can choose the external pressure coefficient for 3D wind. You can choose to use the CPE 10 or CPE 1 values, which are represented in the tables of the code. One thing to keep in mind is that these parameters are taken into account for the full model, and you cannot set this up separately for different load panels. With the option right below, you define a correlation between the leeward and windward side. You will notice, depending on the ratio of the height and the depth, that the resulting force will be multiplied by a value 1 or 0.85. If the ratio is between 1 and 5, that will be interpolated between those values. We will leave it activated for now. Right below, we will find some properties which we will discuss later on for canopies, so right now we will ignore those and continue with the width of the structure. The width of this model is equal to 42.5 meters. This width is used to define the distribution of the peak pressure over the height of our model. In this case, our width is larger than the height, so we will find us in the category on the top, where the peak pressure is constant over the full height. We will discuss a different example later on, where we will find the two different categories represented. The reference level of terrain, which is the option right below, is used to define a height below the global coordinate system, so below the plane z is 0. No winds will be generated below the z is 0 plane, so therefore your structure can be located on that plane and any structure underground can be positioned below. In this model, we assume that the reference level is equal to 0 meters. All other properties you find here below are used to calculate the peak pressure value. One thing that is read from our structure is the height. Now we will change a few parameters here. For example, we change the basic wind velocity to 30 meters per second, and we will modify the terrain category to be category 2. One thing I want to mention here is that the options you have here are dependent on the annex you chose. For example, for the Dutch annex, the basic wind velocity is dependent on another property. With the properties we defined here and the height of our structure, which is 12.5 meters, we are able to calculate the peak pressure. In this case, I calculated this manually, and we will be able to compare this value of 1.404 kilonewton per square meter with the value that SCIA will show us later on. The wind data is created, the types are set, and the annex parameters are checked. Now we can actually create our wind loads with the 3D wind generator. With the generator, we firstly create the load cases to run the generator afterwards to create the loads itself. When you add load cases, you will find 4 different directions that are created with 4 different load cases assigned to it. This takes the pressure and suction of both the external and internal pressure coefficients into account. The internal pressure coefficients are set at the outer end of the table. You can choose to deactivate some options when wanted, and you can even insert new lines with different directions when you want to do so as well, or override the existing ones with another direction. Below, you will find that there is an additional option for load cases for dual-pitched roofs. In this case, we have a dual-pitched roofs, and we will take a look into the direction of our ridge, and that will be the global Y direction. So therefore, that's the direction we choose here. If we now continue, we know that 16 default load cases are added, and for the dual-pitched roof, 16 more are created according to the code. Now we run the generator, and we do know a warning will pop up about those awnings. Not every annex that we have has a specific guidance for awnings, so because right now we don't have one, the German annex is used. That would be fine for now, so we press OK to make sure the wind is generated. Now that the loads are generated, we can take a look first into our load cases, where you will find that all load cases are available and that you can check the different properties linked to those. For each one of them, you will find the wind direction, the internal pressure coefficient, and which one that is actually used for this load case. We can also check the load group because all wind load cases are placed in an automatically created group, and that group will have a relationship exclusive and a load type wind. This relationship exclusive will make sure that our wind load is not combined in an automatically generated combination. If we now move through our different wind load cases, you will immediately find that different colors are used. By default, blue is used for pressure, orange is used for suction, and green will be used for the friction force, which you find in wind load case 5. The wind in wind load case 5 is positioned 90 degrees, so according to the positive Y direction. For that friction force, which I have selected right now, we will find that a value of CPE 0.01 is found, which is equal to the friction force that we selected before in the wind data. Apart from going through the loads, we can also change some parameters which are visible. This will allow us to show us some wind data, which is calculated to verify the created wind zones and so on. To do so, we go to the view parameters and we make sure that the label is toggled on. We can choose a few different parameters to visualize, but I will start with the peak pressure, since we can verify it with the value we found before. When we apply this and we check our model, we find that the zones are represented in view, but we also find the value QP, which is shown in view, which is of course our peak pressure, which is equal to 1.4 kilopascal, which is the same as we calculated before. The zones that you see on screen are calculated automatically based on the code parameters. Since the wind is going in the positive Y direction, we find our zone D at the front, our zone E leeward in the back, and on the side we will find zones A, B, and maybe C, depending on the height and depth ratio. To take a more detailed look into these zones and the related external pressure coefficients, we will take a look into 3D wind 1, which is a wind load according to the positive X direction. I will deactivate the peak pressure from view, but I will activate the external pressure coefficients. I will mostly discuss the walls and the roofs, so therefore I will also choose to hide the awnings. I will select the 2D members and make sure they are hidden from view. To check the CPE factors, we will first check the height and depth ratio, which in this case for this direction is equal to 1.04. For the D zone, we find a factor of 0.8. For the leeward side, a factor of 0.5. For zone A and B, a factor of 1.2 and 0.8. The sign used for these factors in SCIA Engineer depends on the orientation of the load for the local coordinate system of the panels. We can also take a further look into the geometry of these zones, which is also defined based on the depth and the height, but also on a parameter E, which is in this case equal to 25 meters. Since the parameter E is larger than the depth, only zone A and B are created, and the width of zone A is E divided by 5. And this is also something which you can find in SCIA Engineer by taking a look into the geometry. We will be able to verify this for a different load case as well, and we will choose the wind in the positive Y direction. The height and depth ratio will change to 0.29, which makes sure different zones are created, A, B, and C, and that the values for CPE are interpolated values. Now we can take a look into the geometry of these zones as well, more specifically of that long wall, and there we find that the value E is smaller than the value D, and therefore 3 wind zones A, B, and C are created, for which the width again is defined based on the parameter E. Again, you can check this geometry by taking a look into the SCIA model because those lines are indicated. We will not be checking every part in detail, but you will find something similar for the roofs as well, where you find the zones F, G, H, and I, depending on the wind load direction. Up until now, all these zones are generated automatically based on the code. Whenever you find a situation where these zones need to be different from the code, you can change this with the button Edit Zones. On the top left, you can choose for which wind direction you are changing the zones. We will use the wind load direction we were looking into right now. And below, you can choose how the zones are created. Right now, Generate is selected, and this is exactly according to the code and the geometry of the structure, and the factors or geometry cannot be overwritten. The first option you find on the top is Template according to the Eurocode. Whenever you activate this option, you will be able to fill out some code parameters. Let's first activate the edges, and now on the top we can fill out the E parameter, the base from which the zones need to be created, and the zone. You can fill out either value you would like to use. You can choose the base, which right now is 1, but if you change it to 2, you will see the direction of the zones will be modified. We will keep using 1 for now, and then you can choose the zone for which you define if the value E is smaller or larger than D, if this is the windward or leeward side, and so on. And this of course influences the amount of zones which are created. The external or internal pressure coefficient needs to be filled out manually below. Lastly, you will also find the option Manual Design at the top left. With this option, you can define everything yourself. You do not need to fill out the E parameters, but you can choose the base that you are using to create your zones manually. You can choose to edit those zones by dividing and joining those zones. For example, for zone A, at the end, we can click on the button Join to join it with the zone B. You see once it's joined that the third zone A is removed. If we now want to create a new one, we can click on the button Divide. A new zone will be created, and in this next dialog, we can modify the parameters. With each line, you can define an edge of a zone based on a reference edge. For the first line, the reference edge is edge 1, and the edge is parallel to it with a distance in between of 9,600 millimeters. If you create a new line parallel to edge 1 with a distance of 1,000 millimeters, you will find that that new line is created. This will not move the already existing line that you find for zone B. If we change the reference edge, you will see that the zone is created in a different direction from a different edge. If we now change the reference edge to edge 3, you will notice that the new zone will always be created in this zone B, so it will divide the last zone found. We will keep using edge 1 for now, but I will not save these properties later on. You can keep dividing this when wanted, and one thing I haven't shown you is that instead of using parallel lines according to the reference edge, is that you can also change the division type to horizontal or vertical. If we change this now to horizontal, you can see that the direction changes on how the zone is divided. Let's put this back on generate because we are going to use the code generation and regenerate the wind loads so that none of our changes are taken into account. Something we haven't checked yet at this point is the internal pressure coefficient. This one is defined automatically in the load case, but we would suspect that it is influenced by the openings in the load panels. If we now activate the internal pressure coefficient, we will notice that the exact values, as we indicate them in the load case properties, are taken into account. So this indicates that the opening we created in the load panel at this moment is not taken into account for that internal pressure. To take this opening into account, we actually need to change the wind data properties, and there you find that you need to activate the option openings. Once this is activated, you can fill out the area of the opening, and in this case that is 8.5 meters times 5 meters, so 42.5 square meters. You can also activate the option dominant face whenever you have a face for which the amount of openings is twice as much as all the other openings on the other faces. We will of course need to change this property on both sides of our model, and then we can regenerate the wind to take a look into the influence of this setting. Once the wind is regenerated, we see that different values are found. For wind in the positive y direction, a value of 0.31 is found. For the wind in the positive x direction, we find a value of 0.12. In what follows, we will take a look into the generated loads on those columns, for example. And firstly, I will activate the net pressure coefficient, since here you will find the peak pressure multiplied with the CPE factor minus the CPI factor. Now I will only take a look into the loads on certain columns, so I will change my view so only this load panel and these columns to which the loads are transferred are visible. To do so, I will subtract everything I do not need from my selection and hide what is still selected. To generate the loads, you can do two things. You can select the load panel and click on the action button on the bottom right, generate loads. You can also simply calculate the project so everything is generated immediately. In this case, I will only generate this specific load panel, so I will use the button generate loads and make the loads visible with the parameters on the right. Right now we're taking a look into the wind according to the positive x direction, so we are looking into the leeward zone, which is a zone over the full area of this panel, and we will find that for each column one line load is created. When a line load is selected, you can take a look into the properties, and all external and internal pressure coefficients will be listed, as well as the acting width. The acting width here is found based on the tributary area, which represents the area that is distributed to this specific column on the left. We can recalculate this manually ourselves as well. We have the height and depth ratio, which is around 1, so the reduction factor will be 0.85 on this leeward side. The peak pressure we knew as well as our external and internal pressure coefficient and the acting width. We find exactly the same value, 3.15, in our SCIA Engineer software. You would be able to verify this for the column right next to it as well. In this case, the tributary area is twice as large. The CPE and CPI is exactly the same, so the value is twice as large. Around the opening, you will see that the acting width is smaller again because no tributary area is generated inside the opening. So for the load generation, this is taken into account accordingly. We can also take a look into a different load direction, in this case the positive Y direction. And for this case, you will notice that some columns have two line loads applied. The reason for that is again found in the tributary area. In this case, not everything is exactly the same zone. For this tributary area, it overlaps with both zone A and zone B. Therefore, for each acting width found, a new line load will be created. We can take a look into the properties again. For one line load, we will find an acting width of 2.4 meters, which is the width of zone A. And then for the next line load, we will find the CPE factors of zone B, and we will find the acting width of that part inside the tributary area. We can again recalculate this manually if you'd like. With these factors, we find the exact same values, of course. Again, a similar story can be found on the column right next to it, because if you check the tributary area of that column, we find that a small part of zone C also overlaps with this area. So a small line load with an acting width of 0.75 meters representing zone C is also present on this column. So that is why multiple loads can be defined. As mentioned right in the beginning of this webinar, right now we were in a situation where the peak pressure was continuous over the full height. Whenever we would be in a different situation, we would notice that the line loads would not be uniform over the full height. In today's webinar, I am not going to show you this behavior for the model we discussed earlier, but I'm going to use a second model created with 2D members. I am using that model to show you how you can find the distribution of this peak pressure for a model with 2D members where you would not have generated line loads which represent your loads. The model you see here consists of all 2D members for which the 3D wind data is already activated and the orientation is swapped accordingly. The wind is already generated in this case, so we will not need to run the generator at this moment. What we will do is take a look into our annex settings and check which parameters we have used. We will use exactly the same parameters as before. The only thing that will be different is our width of the structure. The values below remain exactly the same, and since the height of this model is also 12.5 meters, we will now find the exact same peak pressure of 1.404 kilopascal. Based on the height and the width parameters, we will find us now in the second category, for which the height is larger than the width, but smaller than 2 times the width. On the bottom left, I calculated the reduction factor and the actual surface loads that we will find for zone E in this model. So for the leeward zone of wind load case according to the positive X direction. We can check this in SCIA Engineer by taking a look into the results, which will be the surface loads. Of course, before being able to look into results, we need to calculate our project. And as said before, I will repeat it, we will take a look into one of our walls and we will use the positive X direction as our wind load case. And we will take a look into the leeward side, so the wall in front of our view. The result we will going to be used is the result surface loads, which will exactly show me on a wall for which load case a specific load is generated on my element. So in this case, I select a wall for which I would like to see this information. I change my type of load to the wind load case I would like to check. which is 3D wind 1, I will make sure the value I request is QZ, the surface loads in the Z direction of my local coordinate system, and refresh my results. The value represented right now show what I calculated before. Below the height, which is equal to the width, we find a value of 0.89 kilonewton per square meter. Above that, we will find 0.99 kilonewton per square meter for the zone. You will also notice again that the load was still uniformly shown. So this is the way you can evaluate this. Now let's take a look into another possibility where the z coordinate is equal to 20 meters. So the height is modified in our model. When we do so, we are finding ourselves in a new category, namely the category 3, for which our peak pressure will be redistributed over the full height. On the top and the bottom, you will find a uniform load, but in between, some strips are generated, and for each of those strips, the peak pressure is recalculated, and thus your found surface loads will be different. You can find my calculation on the bottom left, but it's all similar, except for the fact that for each strip, I recalculated the peak pressure, and then based on that peak pressure, I found the exact factor used for the surface load. We can now check exactly the same in SCIA Engineer by recalculating our project and again taking a look into our surface loads. The procedure is exactly the same. I go to the result surface loads. I make sure only this wall is visible since I'm only checking one wall at this moment, and I will refresh my results. This will show us that right now the peak pressure is different in that middle zone, and you will see that that value is calculated for each of those strips. Now the color in which this is shown depends on the drawing setup on 2D. If you would like to modify this to the rainbow colors, for example, you can change these colors to smooth, and in that case you will find that the colors are changed. You will be able to change some different settings here as well whenever necessary. Again, the surface load you see is shown uniformly, but in reality, these are the loads that are taken into account. Now we have seen all the cases for which the peak pressure is calculated based on those annex settings and code parameters. We can set our peak pressure manually if you go to the project data, and in the tab Actions, you can choose the wind load instead of according to code to user defined. This will mean that you can fill out your wind pressure distribution manually. You can fill out the height on one end and the pressure on the other. So let's create an example where a pressure of 1.1 is found up until 10 meters, and then above 10 meters we will find a pressure of 1.5 meters, for example. You will see on the left that the diagram you are creating will pop up and that you will see exactly what you have inputted. I see I've wrongly inputted the 10 meters in between, so let's change that. Once this diagram is created, we can simply recalculate the project. The 3D wind will be regenerated during the calculation, and we can check our surface loads again to see if this is taken into account. So let's close our project setting, run the calculation. You can already find a peak value shown on screen, which is different than before. The height of the structure was again 20 meters. So if we now calculate the project and take a look into the surface loads, we should find that the peak pressure looks different than before. In this case, I expect to get 2 different surface loads on this member. We can immediately see that that is the case and that the member has a different pressure up until the height of 10 meters, and above will have a higher pressure. And again, you could change this in the project data with the tab Actions, where you can choose a wind load and set it to user defined. A good reason to use this workflow to edit the peak pressure is to take the structural factor into account. And this is also explained on one of our FAQ pages, where you can see that you need to manually calculate the structural factor, multiply it with the peak pressure, and manually define it. And you will as well need to divide your internal pressure coefficients with that structural factor. Now for our last example, we will take a look into canopies and the different settings we find for those type of elements. We will start with a model where you can find a canopy created with 1D members, and to add a wind load, a panel is added to the top. For this panel, we will activate the 3D wind load so we can check the wind data. And here you see that the type roof is selected automatically. We will need to modify this and change it to a canopy. Then you can select the canopy type. Right now it is set to monopitch. If we check our structure from the side, we know that this is sufficient, but keep in mind that whenever necessary, you can change this to dual pitch. Right below, you can find the blockage ratio, which is a value between 0 and 1 that defines how the wind flow is blocked underneath your canopy. Right now, we will keep using 0. We will also find that the friction force or swap outer surface can be activated when wanted. In this case, let's activate our friction force and let's choose a different surface type. Let's use the type rough in this case. We will find a friction coefficient of 0.02 in this case. The coefficient type that you see, which is net pressure CP, we cannot add it for a specific load panel. We will later on see that we can change it to the overall force in the annex settings. As mentioned before, the annex settings can be found on the top right, and we can take a look into how our peak pressure is calculated and how the zones are defined on our member. We looked into a lot of parameters, but before we ignored the coefficient type and the canopy zone direction. With the coefficient type, you would be able to change this to overall force. With the canopy zones, you can choose how the zones are created. Are they based on the global coordinate system or based on the direction of the edges of your canopy? In this case, we are going to keep using the standard since our canopy aligns with the global coordinate system, except for the angle that you will find. All other options for the peak pressure remain the same as before, so we are going to keep using those settings and generate our 3D wind. Right now we haven't selected the overall force, so if we generate our load case, we should find that all zones are created, and for each zones we will find a CPE factor indicated. Now that this has run, let's take a look into our load cases. When checking the load cases, you will see that you will find some loads for which you have a downwards wind load as well as an upwards wind load. One thing to mention is that the internal pressure coefficient is actually equal to 0. If we go further through our load cases, we will find a wind load for which also a friction force is generated. And you might notice immediately that the factor used here for the friction coefficient is equal to 0.04. But if we would check our wind data, we would find that the factor we selected before was equal to 0.02. This is not a mistake, since this is a canopy structure. That friction area needs to be taken into account twice, and therefore the factor is doubled. To take a further look into the generated zones on a canopy, we will move back to our wind load case 1, where wind is flowing in the positive x direction. And we will go to the top view. Right now, you see that both our net pressure as well as our zones are visible. We will change the visibility to make sure that our view is less crowded. You notice zones C1, A, and C2, and on the bottom you will find B1 and B2 as well. Let's also activate our CPE factors by making them visible, and you will find a value -1.4 for A, -1.8 for C, and -2.7 for B. This would be the same as what you would find in our code table. We know the angle of our canopy is 15 degrees, so we know exactly where to look. If the angle would be something in between the known values, the value would be interpolated. One thing I want to mention here as well is that in our table we find our positive values, because in the code a positive value would indicate a downward acting wind force. This is not the case in SCIA Engineer. In SCIA Engineer, the downward acting wind action will have a minus value because the z-axis is pointing upwards in this case. So therefore, that sign can be different. Another thing to mention is that the zones are created correctly, but in the corners where C and B zones overlap, there are no strict rules. In this case, SCIA Engineer will take the more conservative value. In this case, that means that the corner zones will have the same external pressure coefficient as the zone B. When we take it to the model, we can see this as well, and we can also find that for a positive CPE factor in SCIA, you find an upwards wind force, and for the negative values, a downwards wind force. Now, what we haven't checked is how the overall force is generated. As mentioned before, we can change that into the annex settings, where the coefficient type is changed from net pressure to overall force. Once you selected this, we do not need to edit anything else, so we can press OK to continue and generate our wind load. We run the wind generator as we did before. We will not regenerate our load cases, and we will find now that our overall force is generated. And we can go through a few load cases as well. Right now we're looking into 3D wind 4, which is again wind in the positive x direction. The same for 3D wind 1, but you will see, of course, an upwards or downwards overall force can be found. And we can check the same for wind in the y direction. Now we can take a look into how these overall forces are created. And in this case, you can find these calculated based on the depth of our element, which is in this case 7 meters for the positive x direction, the peak pressure, which I calculated in this case, and that overall force factor, which we found in the table as we saw before. For 3D wind 1, so wind in the positive x direction, we would find a value of 4.76 kilonewton per meter. The position of the load is based on the image on the left of this slide. There you find that the position is the width of our member D divided by 4. And based on checking the geometry in SCIA Engineer, we would see that this is correct. If we move our load to 3D wind 1, we will also find the exact same value as calculated, 4.76 kilonewton per meter. This concludes all our examples. In what comes next, I would like to briefly show you what you can add of data in a report. And I'm going to do that for our very first example. I opened a new empty report to which I'm going to add the 3D wind generator data. By double-clicking it, it will be created, and by regenerating, it will generate all the data inputted. On the top, you will find the code references. Right below, you will find your wind pressure calculated according to the code with all the code parameters that you edited. You will also find the correlation between zones D and E is represented with a check mark or a cross depending on if it was activated or not. To edit a table, you can double-click on it and it will go to the edit screen. In here, you can choose if you want to add certain properties or remove them by selecting them and hitting delete on the top. That should allow you to remove certain parts. And if I now remove a big chunk of this table, you would notice that it's immediately updated. We can do exactly the same for the tables below, where you can find the wind data. And you would be able to add a certain column with the tab property. For example, in this case, we can add the type 2D member again, which you can find on the top of this list. It was already added to this list, but let's do it for an example. And keep in mind that depending on if you use a canopy or not, that you can add the blockage ratio when wanted. If we now double click on 2D member and I press OK, this will again be saved, and you will see that that 2D member is added to the outer end. In this table, you also find the type of the members, like wall, roof, and awning, the roof type, and if swap outer surface was activated. In the last table, where you can find your internal external pressure coefficient, you can do exactly the same. If you want to edit anything, you can double click on the table and you can find all the properties listed in this next dialog. We will not be editing this table, but if we take a look further into the data of this table, you will find your internal and external pressure coefficient with all the zones for each wind data property. With this last piece, I will conclude this webinar, and I would like to thank you for joining today. If you have any questions which were unanswered today, please do not hesitate to reach out to us through our support.